Hi guys, and welcome to this first video on sequences. This video will only cover the basics of sequences. However, in a later video, we'll go more in depth. In this video, we'll be talking about the basic terminology in regards to sequences, as well as some notational stuff, such as sigma notation, as well as how we notate individual terms. In future videos, we'll be talking about the arithmetic and geometric sequences, so make sure to stay tuned for those as well, as they are really important and will be commonly tested in school and in competitions. We'll start with some basics. First of all, what is a sequence? A sequence is a list of numbers, but it's not only that. It's a list of numbers that have some special pattern. For example, 2, 4, 8, 16 is a sequence because they have a pattern, as 4 is 2 times 2, 8 is 4 times 2, and 16 is 8 times 2. However, some random list of numbers like 10, 7, 11, 1 is not a sequence because there is no pattern. This is commonly confused with a series. Although these two terms are extremely similar, series is a little more than sequences. A series is also a list of numbers with pattern, but in a series, we mainly care about the sum. So series can be thought of as sequences plus sum, because we care about sum. The final terminology might seem really simple, but a lot of people seem to have this confused. The final terminology is a term. A term is one element of a sequence. For example, in this sequence, 2 would be a term. 8 would be another term. However, their sum is not a term. A term is only an element in the sequence. Alright, so now I'll be talking about some notations that are commonly used within sequences. Now I'll be introducing some notation that is commonly used with it to describe sequences. So, in sequence A, we usually represent the nth term as an. So in other words, the first term of sequence A would be a1, the second term would be a2, the third term would be a3, and so on. In other words, if we have a3, that is the third term of sequence A. Let me give an example. Let's say there was a sequence with terms 3, 6, 9, 12, and 15, and it ends at 15. 3 would be a1 because it's the first term of sequence A. Of course, that is if we set this sequence as A. A2 would be 6 because that's the second term. And then A3 would be 9, A4 would be 12, and A5 would be 15. Note that here, n is a constant, and in notations we always use n, but a sometimes gets changed around. Sometimes you might not see a1. Instead, you might see something like g1, g2, or you might even see weird things like d1, d2, e1, e2, and all of these are okay. The only thing that is not okay is the n value here. The n value here, if you don't know what n is, you must write it as n. And if you know what n is, for example, if you know that this is the fourth term, you have to write it as a number. Now I'll introduce the second notation, which is sigma notation. This is more commonly used within series as it deals with a lot of sums. So when I started dealing with sigmas, I thought that it was trying to trip me up. And I believe that a lot of viewers also think that. Why use sigma notation when you can easily write something with ellipses like ... Well, it's not that simple. First of all, writing using ellipses still is really long. Like you would still have to write a lot of terms, but at the same time, it's incredibly imprecise, as you don't know what is inside the ... Some people might think that it is 4 plus 4.5 plus 5, while other people, maybe more intuitively, might think that it is 4 plus 5 plus 6 plus 7. Although this might not be true in something like this, it could be true when you're dealing with more complex equations like a1, a2 plus dot 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 plus a99, a100. There was one time where I wrote this and there were actually two different interpretations. One interpretation is all permutations, so a1, a2 plus a1, a3 plus a1, a4 plus a98, a99 plus a98, a90, a100, while some people just thought that this meant a1, a2 plus a2, a3 plus a3, a4. But those two equations are completely different. So this creates a need for a sigma notation. Well, how do we construct a sigma notation? First of all, we notify the range of the terms. Are we adding the first term, second term, third term, dot 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 to the 50th term? Well, if yes, great. We put I equals 1, which is the starting term on the bottom, and 50 on the top, which means that we start from adding the first term, and then we add the first term to the second term, to the third term, to the fourth term. And we do that until we add to the 50th term. What if we're adding from the second term of the series to the 100th term of the series? Same thing. We start with the second term and we add that to the third, the fourth, the fifth, all the way to the 100th term. But there are infinitely many series from the first term to the 50th term, or from the second term to the 100th term. Therefore, we need to specify the series to the right of the sigma. Well, how do we do that? We have to represent that in terms of I. As we're adding the first term to the second term to the third term, all the way to the 50th term, we can think about varying the I from 1 to 2 to 3 to 4 to 5 to 6, all the way to 50. Well, in the right of the sigma, we have to match the term to the number in the sequence. For example, I equals 1 to 50, 2i would equals 2 times 1 plus 2 times 2 plus dot 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 plus 2 times 50. Why? Because we're adding the first term to the second term to the third term to the fourth term. But each term is twice the term number. Another example is if we start from I equals 1 to 50, but instead we do 2 to the ith power. This would result in 2 plus 2 squared plus 2 cubed plus dot 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 plus 2 to the 50. Why? Because we're adding the first term to the 50th term of a series. But each term can be represented as 2 to the I. So we get 2 squared because I is 2 cubed because I is 3, and 2 to the 50 because I is 50. Note that although we set I equals 1 here, I does not always stay to be 1. That is just the starting value. Like in programming, we only set the first instance of the variable, and in the future, we don't have to recreate a variable. We can just change the variable. This is the exact same. We set I as 1, and then every time we change I from 1 to 2 to 3 to 4 when we're adding the series up. This is all for sigma notation, and this is all that we'll be looking at today. For arithmetic and geometric series, please tune in, and as that will be covered next in our channel. Thank you for viewing Connor's Math Land, and goodbye.